Yeah, so I'm going to be talking about possibilities of putting something like ChatGPT, large language models, on phones in your pocket, and a large part of that is to do with quantization. So the talk is basically all about quantization. A little bit about me. I work for a company called Expedera, and we're a startup and mostly based in the US, in California. So we've got an office there with like 50 people or so. We've also got an office in Taiwan, an office in Shanghai, office in Singapore, and now one in Bath too, as of 6 months ago. And it's like 50 yards that way. We're at the Guild, next to the Guild Hall. So what we do is we do designs for processors for AI. And as an example for this talk, I'm going to talk about Zephyr 7B beta as the model. This is a model that's based on Mistral, which is the current kind of champion of 7 billion parameter models. So it seems like a few people have heard about it. And the beta is the first one that came out. This was alpha and this beta. The beta is slightly better. And so you can kind of see this is like some challenges, I guess, that the Zephyr people picked. So they might have picked ones they're good at, but they're doing much better than other things that are similar sizes, and they're kind of doing almost as good in some sort of points as these much bigger ones like GPT 3.5. They're quite a distance from GPT 4, but yeah, there's like 2 orders of magnitude less parameters in them. And the kind of interesting thing about this is, if you look at, this is like a sort of measure of the different skills this thing's got and how good it is at them. And you can see that like GPT-4 is definitely beating it in coding and things. But up here in these sort of more fluffy things, it's kind of doing just as well. And these are possibly some of the things you might actually want to have on your phone. You might want some writing or bold play, or those sort of things on your phone. So this is kind of interesting to me. And you could imagine that people would really want something like this on their phone where they know they're not sending the data off to the cloud. It's all kind of private, and they're just interacting with this thing in a known way. So that's what I'm going to be talking about. And let's quickly run it up. Oh, everything's changed size since I plugged the window in.
I saw something online referring to it as like a humanities graduate. Right.
Right. Yeah, so the llama in here is not talking about so llama is a model from Facebook, and llama 2 is the latest model from Facebook. But it's also an architecture, and so these people at llama.cpp have implemented llama and llama 2, but they also support a whole lot of other models. And one of the models they can run is the Mistral. So this is it running, and you can see somewhere up here that it's trying to use 13 gigabytes of memory. That's because it's like a 7 billion parameter model, and each parameter is 2 bytes. So multiplied out, and what happens if you try and run it on this is it fails because it's run out of memory, because I've only got 16 gigabytes in this MacBook, and so it just can't run, which isn't good because that's more powerful than a phone. So there's 8 gigabytes of memory in my phone. So this is kind of by the end of the talk, we will be able to run it on there. So let's go back to here.
So it'll also run on CPU rather than any GPU resources.
It is running on the GPU bits in the Mac, yes. But in fact, I mean, the guy that wrote this llama.cpp basically did it in order to run it on his Mac. So the Mac is like the first class citizen in this thing. So in order to explain all this, I need to explain a bit about transformers, which is what large language models are based on. Who here is familiar with transformers? Okay, well, this is a picture ChatGPT drew explaining it. So there's a number of these throughout the things. And none of them are very explanatory, but the text is kind of good. But let me go on to my picture of how I explain it. So the job of these things is to predict the next token. That's all large language models do. And a token you can kind of think of as a word, but it's not quite a word, it's a bit of a word, but you can think of it as a word. So you put the words in here, and hopefully you get the next words out of the top. So you put in what is the capital of France, and out of the top, hopefully you get the capital of France is Paris, and that's all it is. So in a bit more detail, they take these tokens, and there's 32,000 in this case, possible tokens that they split the words up into. And you look that up there, and you end up with 4,096 numbers, which is the model's idea of what the token means in a whole lot, in all of these dimensions, 4,000 dimensions. And you call that an embedding. And then you go through these layers, transformer layers, and you get up to the top, and you sort of map it back into 32,000 numbers, where each one is the probability that that number is the next token. And then you just look through and you say, oh, that's the most likely one, or you don't have to pick the most likely one. If you want to be a bit crazy, you could pick one a few down. And then you get the next token out. So hopefully that will say the and then after you've got that out, you put it back in, and hopefully it'll say the next one will be capital. So yeah, that's all that is. Inside each transformer layer, there's a load of maths. So these 4,000 numbers kind of go in here, and then they get multiplied up by a whole lot of other numbers to form these things called a key, the value, and the query. And they go into this block called self-attention, which I'm not going to talk about really, which sort of finds the correlations between them. And you get out another 4,000 numbers. You go into this layer here, which multiplies the 4,000 numbers again by a whole lot of other numbers. You add on a bit from there, but that's not really important. Then you go into this thing called a feed-forward network, which is kind of similar things going on here. You get 4,000 things in here, you multiply them by a lot, you end up with 14,000 there, 14,000 there. You go through this function, which is a non-linear activation function, it doesn't really matter. You multiply that, 14,000 numbers, 14,000, and then you're back down to the 4,000, which is coming out of there. And then, so there's 32 of those in this 7 billion parameter model. But the point of this, the main takeaway is there's a lot of numbers in here. So in this kind of chunk here, there's 42 million numbers that you've got to deal with. Those numbers are called parameters or weights. Mostly I'll call them weights. And in this chunk here, you've got 176 million. So if you add those two numbers up and then multiply by 32, you end up with like 7 billion parameters. So yeah, what is going on with all these numbers? This is ChatGPT explaining it again with his helpful pictures, but my pictures are less beautiful, but hopefully more understandable. So we've got these things, the activations. These are the 4,000 different numbers that are being passed about, and we've got the weights or parameters, which we've stored away inside the network, and those are some sort of numbers. And we just multiply that number by that number to give another number, and that by that to give that. And then we add them up, and then that's the output, which is being passed on to the next thing. So yeah, it's not very complicated, you just have to do it a lot. And the next thing we need to talk about before we get to the meat of it is floating point numbers. These are some lovely pictures, again from GPT-4. Who knows what floating point number is? Everybody. Oh, well, I'll go through it really quickly. So that's more ChatGPT nonsense. So this is not a floating point number, this is an integer. You can imagine in a computer if you've got like a certain amount of space to store each number, and I've done it in decimal here to make it more understandable, but obviously in the computer it's in binary. But so if you've got 4 digits there, you can store any number between 0 and 9,999. But the problem is, what if you want to store a number like 1.45? You'd have to just shove it in as 1. And that doesn't work for training these models, because the whole training process works with, there's a load of those numbers in there that are kind of random to start with, and then you put in the training data, you see how wrong it is, and then you sort of push backwards through the network, fixing up, trying to make it a little less wrong. And if you try and do that when you've got big steps in your numbers, it just doesn't work. You need to be able to tweak each number. So this is another way of storing numbers. This is floating point, I guess. So you decide that one of your numbers is going to be where the decimal point goes, and the other numbers you've got left over are going to be the actual number you want to store. So in this case, if you put 4 in there, the decimal point's there, and you can store 1.45. But you can put the decimal point there and get a really small number, or you can put the decimal point way back there and store a big number. So these numbers are not being stored, it's just the 4 numbers still. And actually inside a computer these things are either 16 bits or 32 bits or 64 bits sometimes, but mostly 32 bits normally and 16 bits mostly in machine learning. So yeah, let's talk a bit about quantizing these weights. So the idea here is to take these big floating point numbers that are 16 bits and to try and store them in a smaller amount of space. So in this example I'm trying to store them in 4 bits, and this is an integer, 4 bits integer, and this is the binary here, and it can store all these values from -8 up to 7, so there's 16 values it can store. And the way we can do this is we sort of say, here the numbers go kind of up to 300. So if we divide by 300, we'll get numbers that go up to 1. Then we multiply by 8, we'll get numbers that go up to 8. So that's what you do. You multiply by 8 over 300, and you end up with those numbers there, which would fit in the range there. So then before we use them, you have to do the opposite of that. So you just multiply by the opposite of that, the inverse, and you end up with these numbers, which, well, they're kind of the same as those, but not quite. So you hope they're close enough that the error is not a problem. But the issue here is that we haven't really used all the range there. Oh, I should say that as well as storing these numbers, you also need to store that number, which is the number that you need to get back the values, so as well as these. But usually that's not that much of an overhead. But the problem is, yeah, we've missed out all of these numbers here. We could have used those. So a better thing to do usually is to not only scale the numbers, but have a 0 point as well. So in this case, it's 125 is the number to use, and you end up with something that's roughly goes from plus 175 to minus 175, so it's centered on 0. And then we can multiply it by a different number, a bigger number, small, I don't know. And then you end up with a nice range where you've used all the numbers, and to get back again you have to multiply it and then add on the number you took off before, and you end up with these numbers, which again are not the same as those numbers obviously, but they're closer than they were in the other case. So the drawback, of course, is that you not only have to store this number now, you have to store that number as well. So you've got 2 number overhead. So, yeah, I was going to do a little demo of those ones. And this is all based on this llama.cpp, which was written by this guy there, Georgi Gavnov, I guess. I couldn't find him saying his name anywhere, so that's as good as we get. And this is a version of the llama written in C++, mostly C actually, but there's C++ in there as well. So let's give that a go, and we'll run the 6-bit one. So here you can see it's a lot smaller. It's 5.6 gigabytes. So it's loaded up, and now we can type at it. And hopefully it will say something. Yeah, it's quite excited. Yeah. Well, so it worked. Let's get my glasses actually. And you could ask it more complicated things. Got some had some examples somewhere that people were putting into these things. Let me make this a bit bigger. Let's try this one. Oh, that's interesting.
This is the role play.
What? Well, I don't know. This is a kind of moral question as well. So Llama 2, actually, I ran it this morning, and it said definitely the AI, because the human, the AI, you could lose important information, and the human is probably, it might be okay, basically, it was saying. So it's quite interesting. But this one's sort of hedging its bets a lot more. Yeah. But
This is literally just the 7 billion model with quantization applied. No
yes,
checks.
yeah, no,
Impressive.
yeah, and this. Let's try. There's a 4-bit one here. See what the 4-bit one says. No, this is.
It also makes me think like, it has some way to get worse. Like presumably you can like quantize all the way to like 0.
Well, we'll get there. don't worry.
Okay. But like this is still pretty good.
Yeah. Oh God, it's worried about its thing if it's in a small bit of the. Yeah.
It's pretty good, isn't it?
Yeah, and we do. I do have the 2-bit one here. Q2. Yeah.
It's why I always find it hard with all those metrics, because they don't really give you a qualitative feel.
Yeah, I've got some more scientific thing on the next slide. So, well, it's really thinking about it here. The 2-bit one.
I think it's actually faster than ChatGPT 3.5 or something.
Yeah.
It seems so fast.
Yeah, well, it's doing a lot less work, so it should. But then it's running on my MacBook, so.
But it's amazing the 2-bit one kind of works. That's
Yeah,
well,
yeah. We'll get into why that is as well. So let me go back to the presentation. I've forgotten if I wanted to actually show more things, but right. So this is the more scientific measure. Of perplexity. Is anybody familiar with perplexity? Okay. So the idea is that you get some text that you know is good text, and most people use the text set called Wikitext 2, and you give the model sentences out of the text, and you say, what's the probability of this sentence occurring? And hopefully it'll be quite high because it's good text. So it's sort of a measure of how surprised the model is by your sentences. And if you fed it junk, it should be saying this is junk, but we're feeding it good stuff, so it should be saying, yep, that's good. And you can see that this is the difference in the perplexity from the original floating point model. So you can see at 8 bits it's almost identical. At 6 bits somehow it's better, but that might be just some sort of artifact. And then it gets worse and worse and worse. And by the time you get to 2 bits, it is quite confused by what it's seeing. There's various, I'll go into what kind of tricks they're playing later in these quantizations. But you can also see the sizes. So we've gone down from like 13 gigabytes down to 6.7 here for the 8-bit one, or even 5 for the 6 with almost no change. And then down to the 2 is getting really small.
That's amazing. You just lose 6 gigabytes and it's perfectly
Yes. Yes.
The redundancy is huge.
And this is another graph from Georgie. This is actually about llama 1 rather than the model I've been showing you. So it's not as good overall, but it's showing you kind of the relationship between the size and how perplexed it is. So for the 7 billion parameter model there, if you quantize it heavily, I think this is probably a 2-bit one. It gets very confused, and then it slowly gets better as you're quantizing it less, up to a point where it's there, which is still much smaller than the unquantized one. But it's almost as good. And that makes it, this lets you see that when you do this for the 13 billion parameter one, if you quantize it right down to 2 bits, you end up with something that's kind of much less clever than the 13 billion, but it's still just a bit better than the 7 billion. And it's the same size, obviously. And this sort of pattern repeats itself as you go to the bigger and bigger models. So
it's like an inherent scale hierarchy in there.
Yeah, there's something suspicious going on there, because those points are very close together. Although there's some weird step here which I don't quite understand. I guess maybe there isn't a quantization that would get you that small, so that's why that step exists there. But I think he also said that this shows that it's easier to quantize bigger ones, but I don't quite understand that. Anyway, an interesting graph. So all of those examples before, I was quantizing the weights, but the activations, those numbers that are passing through, they're all still floating point 16-bit floating point numbers. Which is fine for things like MacBooks and GPUs and things, because they've got a lot of floating point processing power in there. And the real limiting factor is basically how fast can you read the weights out of memory. And you're sort of leaving processing power on the shelf in this case. But if we're thinking ahead, or actually designing our own processors to go into phones, then it'd be much nicer if we weren't using floating point numbers for the activations, because it's much more power efficient to be using integers on both sides, to just be doing integer maths than having to do floating point. Even if one is an integer and one's a floating point, it's much more costly to do than if both are integers. So it would be great if we could also quantize the activations. So various people are looking at this. And this first lot of people are LLM.int8. And what they did is they looked at trained models, not massive models, but, they did look at big ones, but they started off down here. And, I guess everybody started off down here with these smaller models that were open source. And this graph is sort of showing that this is an 8-bit quantization of the activations and the weights. And it was doing fine as the models grew and grew and grew. And then suddenly, when they got to about 6.7 billion, they say, it started crashing and stopping working. And the reason that this has happened is that they are seeing outliers appear. An outlier is like most of the activations are kind of down here, and then there'll be one that's up as a spike. And then you can imagine that if you're trying to put them into those quantization numbers that I was putting them in, if you're trying to put one up there and all the other ones are down here, all these ones are going to be either 0 or 1 or whatever, and then you'll have one number that is the big number. So it stops working in the presence of these outliers. And yeah, the paper is really interesting because it sort of starts saying that as the number of parameters increase, the number of these outliers, which start off, there's only a few in each layer, they sort of spread to all layers, and they sort of spread to a certain number of dimensions. So there'll be like 7 dimensions in each layer. And yeah, it's weird things are happening. But anyway, the way they solve this is they split the calculation into 2 parts. So there's one part that's dealing with the normal numbers that they're seeing, which they use 8-bit maths for. And then there's the other part which is dealing with these outliers, and they use 16-bit maths for that. And they claim good results, and they're sort of tracking the original model there using this. The problem with this is that it's very hard to actually implement this sort of thing efficiently, because you've got to switch between the numbers and you've got to know which numbers are in which part. So this sort of hasn't taken off that much that I've seen.
Is there like an intuitive explanation for what those outlier features are doing?
No,
They're not
no,
those?
that's what. Yeah, so yeah, the next one's got some pictures of them as well. So this is the kind of activations shown by dimension there, and the kind of values, the absolute values, and most of them are kind of wiggling around here. You can't even see them. And then there's these few ones that are like big spikes there. And these people have SmoothQuant, and their solution is to kind of take these spiky activations and the kind of smooth, the weights tend to be smooth, and sort of push some of this spikiness onto the weights. So the weights become more spiky and the activations become less spiky, and you can quantize both of these. It's a little bit harder to quantize the weights now, but it's still fairly easy. And this is a little example of what they're doing. So in the original, they had like 16s in this thing and 9s, and they've sort of squeezed it. So they've replaced the 16 by 4s and 4s in the weights. So yeah, this is a little bit weird because they're exploiting these properties that people don't understand why the properties are there. So you can imagine if somebody does figure out why they're the outliers, then you'd be much better off having everything an outlier, because you'd be able to pack more information in there, because there's not that much information going on in these bits. So yeah.
Have you seen anyone using kind of like trying kind of exponential or kind of logarithmic?
Yeah, there are different number systems. They're sort of being held back by the fact that GPUs don't support them. So there's somebody who has something called normalized float 4s or something, which is a sort of logarithmic sort of.
Yeah, because if you've got these big outliers, then actually kind of like an exponential scale will actually give you the coverage.
Yes.
If you just use logarithms, it just goes back into addition anyway, so you can kind of just.
Yeah. But this, so I don't think we've really seen the end of this, and I'm not sure whether it's something you could count on, because I think the outliers, there's going to be more outliers in the future. So I'm going to go back to talking about quantizing the weights again in a bit more detail. And all of these models that I've been showing you have been coming from this person called the Bloke, who's Tom Jobbins, and he quantizes models apparently for a living these days. He's got, I think, £1,700 a month income on Patreon and some sort of grant from venture capitalists in the US for quantize. And so there's just hundreds of quantized models on here, some of which I've showed you. And the ones I've showed you are the ones that are running on Macs and CPUs, and they're in this format called GGUF, where the GG stands for Georgie, whatever his name is. But there's other formats there as well, and these are kind of more suited for running on GPUs. There's AWQ and GPTQ. So I'll just quickly explain a bit about that. So AWQ is activation aware weight quantization. And what they do is they put some training data through the network, and they look at the activations. And again, there's this outlier thing going on. So some of the activations are much more important than others of the activations. And the numbers like actually less than 1%, it's maybe 0.1%. And if you remove those 0.1% of these salient things, then the whole thing just falls apart. But if you remove a random 0.1%, there's no effect at all. So there's something important about these. And so, I mean, they started off by just keeping those as floating point, which fixes any issues, and you get the same perplexity as the FP16. But you can do a bit better by, if you sort of average this out, then you can scale your weights before you quantize them to sort of handle that extra activation. So that's what they're doing, and they get really good results. This is it's much better having pictures to see things. So you can see that this is the rounding to nearest neighbor, which is the simplest way you can quantize the things. When I did that multiply, you just see whether you're closer to 6 or 7 and put it in the right bucket. And the W4 means it's been quantized at 4 bits, as I showed you before. And it thinks that the man's holding a baby elephant. Obviously it's not, but their one gets it right with the same size weights, so 4-bit weights. And yeah, obviously they picked ones that they got right, but so that...
Yeah, because these are really fascinating, because there is something in there of these kind of high-powered activations is pushing it towards a different part of the space that seems to be like a correct space.
Yes.
But it's like a nudge somehow, because you can tell what it's doing in these RTN numbers and how it's getting close and then not getting. It needs to be kind of pushed away from one manifold almost to another one.
Yes. Yeah, it's very interesting. And the GPTQ depends on some very complicated maths, which my son was trying to explain to me, but I did not understand. So. In my terms, this sort of started out with something called optimal brain surgeon, which is a way of looking at neural networks and trying to knock out weights, so just totally getting rid of them, so you don't have to calculate them. And this is more targeted. This is another picture from GPT-4, so it's all a bit bizarre. But the idea there was, once you got, there are some weights that don't really matter, so you can just knock them out. And then this was sort of extended to be optimal brain quantization, which said that if you look at there'll be one weight that you can quantize and it'll have almost no effect. So you do that one, and then you go on to the next one and the next one. Hopefully you'll get to the end and everything will not have changed too much. Because after you quantize the weight, you sort of push the errors you've introduced onto the other things in there. But what GPTQ figured out is that that's all very well, but it's impossible to implement because you have to do everything serially. You have to do one weight and then the next weight and then the next. And that you just can't do that at these massive scales because it takes too long. So they sort of figured out that it doesn't really matter what order you do them in, because if you do one that you shouldn't have done, if you do them in exactly the right order, by the time you get to the end, you've got a lot of errors because you've done the easy ones first. So, and there's nowhere to push the errors. So you can just do them in a random order, or a fixed order rather. So they do them in a fixed order, which means that you can now do them in parallel because you know all the ones you've got to do and what order you're going to do them in. So that saves a lot of time, and they claim very good results for this. and there's some other maths to do there, which I don't understand. There's something to do with the precision, maintaining precision, so they decompose some matrix. And then they sort of sweep across the rows like that, quantizing whole columns of the like that, which you can run on a GPU easily. So they can do this in like 4 hours, even for many billion parameter models. And they get good results, obviously, much better than the rounding to the nearest neighbor. The AWQ people say this isn't good. They say that when you're doing this, you actually have the possibility that, you're using training data here, a small training data set, to push through and do this stuff. And they say that you might end up specializing yourself too much on that training set and lose your generalization. So that's why they're against GPTQ. But this is widely used, as is the AWQ. So this llama.cpp quantization is extremely dumb compared to those things. So how is it actually working so well? Because it's also kind of on a par. So the first thing they do is they're actually quantizing small groups of numbers. So like 32 numbers, they'll pick the 32, and then they'll treat that block as a little quantization block, and they'll store the scale and the 0 point with that block, which makes it easier because you're more likely to find numbers that are in a small range if you pick less numbers. And the other thing they do is they don't really do 3 bits when they say it's 3 bits. So there's 3 bits here in the input embeddings, but there's 6 bits. In fact, all of their examples, no matter if it says, even if it says it's 2 bits, it's got 6 bits in this linear layer here. And so there's 3, but they've kept the values at 5 and the linear layer there 4. So in that big long list I had, it actually had multiple things for each bit. But so there was Q3KM or Q3KS, and those ones are the different tweakings with the different numbers of bits in different areas. So it can be mostly 3 bits, and then maybe they'll use less 4 bits for that, and that'll make it a bit smaller because that's the kind of biggest thing there.
That's interesting though. So certain bits of the architecture are more sensitive.
Yeah, this is really important.
Yeah. But like the key and the query are kind of like, it's just a general gist of that.
Yes.
And now the input embeddings, they don't seem to be.
Yeah. So these two things are getting multiplied together, aren't they? And then softmax, which is linear. So that's sort of ironing things out maybe a bit, but then it's multiplying by that before it goes to the self-attention. So maybe that's more important. And I think I've got a picture of the 2-bit one as well. Yeah, so again, there's some 2-bit, there's a similar sort of pattern, but here they've kept these guys at 3 bits. So in the feed-forward network, they didn't go down to 2 bits. I think that might be it for the slides. I was going to show you a quick demo of the real true 2-bit and 3-bit ones. So where's the 2? Yeah, this pure one. So I've quantized this. This is no use to anybody, so nobody else has bothered to do it. But it's really small, so let's see what it thinks the capital. What is...
There we go.
Right, so it's gone totally nuts.
Kind of screams from the other side.
Yeah. These changes are coming. The order. What is this movie? Yeah.
This was like back in the GPTJ days. I don't know if any of you guys use GPTJ.
No.
It was like this.
Right. But Oh, it's got trust stuck in a loop there, which is these are the orders. But let's try the Q3 one. This is a real 3-bit Q1. I think this is less mental.
What?
Oh, it's not bad, is it?
It's all lowercase though. Oh, no.
Oh yeah. Somebody, my colleague noticed that on the lower bits it stops using capitals.
Does it also kind of matter on how kind of like popular or how kind of like, so if you're asking a question about Paris,
Yeah.
but if you ask a question about kind of like some random, I don't know, village somewhere, it would kind of.
Oh, it thinks the security guard's life is priceless. Well, have you got a better question?
Maybe capitalization was just following Costas's point. I don't know who said that. But yeah, maybe it's just following.
No, I don't think so.
It's so weird because we're not used to that style from like the super RHF GPT-4, right?
Yeah. Oh, it's totally different. Well, it didn't jabber on at all. Yeah.
I always wonder what is just how regurgitating different bits of Reddit.
Yeah.
You don't know what you're going to get each time. It's like a randomised information retrieval.
So
I wonder if it's possible to probe the 2-bit version. Does it actually know what the capital of Paris is?
Right.
It's just like not telling you.
yes.
Like, I assume it must do, because that seems like quite a fairly basic piece of information. But
Yeah. It must. Well, it's in there somewhere.
yeah.
It's just.
If you give it, can you like give it a prefix? So for the response, you force it to start with the capital of France is,
Oh yeah.
and see what it generates next.
I promised you running on a phone. So
Genius.
maybe this will work. It does sometimes crash, though. It's loading. Anybody got a question for this? Not too complicated.
What is quantization?
What?
What is quantization?
So which one are we looking at here?
This is the 4-bit, sort of medium-sized 4-bit one. It starts out really slow, and the reason
It's a strong start, though.
Hmm?
It's a strong start.
Yes, yeah. And you can see what a token is as well at this speed. So, the reason that it's so slow is that it's actually loading the weights out of the flash into the DRAM inside the chip. And once it's all loaded in, it's sort of kicked out all the other things the phone's doing. We should have asked it about in LLMs, because this is what CD players and things are doing, or the opposite of what CD. Yeah.
It's still pretty good because, like, these are the kind of questions I ask like science graduates. And,
Right.
It's a 4-bit one can answer this as well as a.
Is that enough for it to? It didn't cut. It didn't follow on from the. Oh, it's probably got the context window. Is only. Oh no.
It's not bad.
I was reading there was one paper which has some really interesting bits where you can kind of a bit like the 8-bit and the 16-bit composition. You can kind of certain bits of the output are only require low quantization kind of stuff, and then other bits require the detail.
Right.
So you can actually get away with kind of they're running both in parallel, or like only taking it when it's different. But there's some really interesting stuff you can begin to look at when you run kind of different bits in kind of parallel, or kind of like a submodel
Right. Well, there is a technique for speeding up big models by you run a smaller model. So then the smaller model, you say, give me 10 tokens out of the smaller model, and that's really fast in the small model.
Oh, yeah.
And then you can take those 10 tokens and in parallel you can put them all into the big model. So instead of running one token all the way through and putting the next one in, you run all 10 through and say, what's the chance you would have said this? And it says, yep or no to each token, and maybe you've got 3 right, and so you've made it 3 times faster by doing that.